All right, we are at 21.8, the transformer. Uh, let's share the PowerPoint. And there are times that we want to step up. We want to increase the power, or not the power, the voltage. And sometimes we want to decrease it. So when you want to charge your, you have your little device that charges your phone, you're going from 120 volts to I don't really know what the transformer is. It's probably something on the order of 5 volts or something like that. Some of you may know. I don't know, but it's not 120 volts going into your phone. So you want to step it down, or in some cases you want to step it up. You want to get more voltage than your 120 volts. And we use transformers to do that. So an AC voltage delta V1 is applied to the primary coil, and the output voltage delta V2 is observed across the load resistance R. So we use, you sort of did this in your class, and use a little iron rod between the transformers, or between the coils, to enhance the transfer of the magnetic field to the coils. So you have the primary input, delta V1, and you have your secondary output, delta V2. Now, sometimes it's not a matter of stepping up or stepping down, but sometimes it's just a matter of isolating to where there's no ground connection there's no earth ground connection to the source. That's another case where we use transformers. But when you turn on the power to the transformer, you get the induced voltage shown here. Delta V1 is equal to the minus N1, the number of terms, where N equals the number of turns, minus N1 times delta phi over delta T, the change in magnetic flux over time. You remember, there's no change in magnetic flux, you have no induced voltage. So on the secondary, the induced voltage, delta V2, is equal to minus N2 delta phi B over delta T, the change in magnetic field over time. Well, let's divide delta V1. Let's divide delta V2 by delta V1. So we end up with delta V2 over delta V1, and N2 over N1, and the delta phi delta T over delta T, that disappears. I mean, they cancel out. So, and then if we solve for V2, remember we had delta V2 over delta V1. Well, we bring delta V1 to the other side, and you have N2 over N1. So you can, if N2 is larger than N1, let's say it's, you have 10 turns on N1 and 100 turns on N2, then you've got an increase. You have an increase. You have a step up transformer. Now you might think that, well, we get something for nothing, but that's not the case, because the power is going to remain the same. So I1 times delta V1 equals I2 delta V2. So if you have a step up, you may get 10 times as much voltage, but you get a tenth of the current. You don't have the current capability that you have on the other side, because the power is going to, we have a conservation of energy, so the power is going to be the same. And most of the time, you don't have a perfect transformer. You're going to get 90 to 95% efficiency, so you're going to lose a little bit of power on the other side. And the power companies use this. They'll step up the voltage to a very high voltage. I think, what does it say here? It says like 230 uh, 230,000 volts, but it's very, very small current. The current is very small because you remember power is I squared R. So if you can, if you can cut the uh, the current down, since it's a square term, if you can um, reduce the current by a factor of 10, you've reduced the power loss by a factor of 100 because of the I squared R. And so then they step it up to, high voltage but low current. And then when they get to the point where they go to the next distribution station, they lower it back down to about 20,000 volts, and then step it down to 120 volts when it goes to your your home. And I've seen the fuses that go on each leg. It's usually used a um, three-phase transformer. The fuses that go into those transformers they're very long and very, very big and hefty. You could use them as a weapon if you so choose. Um, and so that's it for the transformer. We're going to get to Maxwell's equations next. That'll be section 21.9.